Hi everyone, this is going to be the first lesson on the topic of chemical energetics, kinetics and equilibria. In this lesson we're going to be focusing on the thermodynamics of chemical reactions which give out energy, chemical reactions which take in energy, and we're going to be explaining that in terms of changes in chemical bonding. So this is essentially the topic of chemical energetics. So before we get started, let's take a look at the learning outcomes for this lesson. So, as I say, in this lesson, we're going to be looking specifically at the energetics of chemical reactions. And so we're going to start by recapping some ideas that perhaps you've come across in your previous years of education in chemistry, the idea of exothermic and endothermic reactions, the difference between the two. And we also need to exemplify that by means of looking at specific examples of exo and endothermic reactions. So in that vein, we're going to be looking at fuels and the combustion of fuels to begin with. And then we're going to look at how can we actually measure the exothermicity or endothermicity of a reaction. How can we measure the energy output or the amount of energy taken in during a chemical reaction? To do that, we're going to be looking at an experimental technique of measurement that we call calorimetry. We're also going to be taking a look at sources of error in experiments involving calorimetry. So, some of the examples that we're going to be encountering, as I say, we're going to start with the idea of combustion reactions. Some of the other examples that you're going to come across both in this teaching video and also in the various other learning activities on this lesson's page on the website, including the downloadable pack of exam questions that is associated with this topic, will be some reactions that we've already encountered in other topics and reactions that we're going to be encountering in later topics. So things like the dissolving of salts in water, neutralization reactions between acids and bases, displacement reactions which we encountered in the previous topic where we looked at the reactivity series of metals, precipitation reactions where we have reactions happening in solution that produce insoluble substances, and these are all either exo or endothermic typically. There are exceptions, but these reactions will always be accompanied by a change in temperature of the reaction mixture, and that will also depend itself on whether the reaction is exothermic, whether it produces a heat energy output, or whether the reaction is endothermic and requires heat energy to put into it. We then need to look at what we call reaction profiles or energy level diagrams for reactions, and we need to be able to distinguish between the energy profile diagrams for exothermic and endothermic reactions. In doing that, we're going to encounter the idea of activation energy, which is essentially the energy required to initiate a chemical reaction, and we're going to expand upon that. And we finally need to look at what is the reason why a particular reaction is exothermic or endothermic. And as we'll find, it's to do with the breaking and the making of new chemical bonds. So there's quite a bit to get through. Let's get started here. Now, as always, I'm joined by a lot of students via the Zoom client. Many of you, once again, have asked a number of very interesting and pertinent questions that I'll be addressing both throughout this teaching video in the recorded segment of this video. But there are a number of questions that you guys have asked which fall slightly beyond the scope of GCSE Chemistry and fall more into A-level chemistry. For the benefit of those of you who are in attendance who've asked those questions, I will be addressing those as always in the Q&A session that will follow the recorded segment of this lesson. But if you're watching this as a recording and you have any questions at all about chemical energetics, you can simply log into the website, and if you're enrolled on this course, you can go to this lesson's page where you'll find the student notes section where you can send me your questions as a private message. If you do send me a question as a private message, typically I'll respond to your question privately within about 24 hours. There's also the facility, as always, on these lessons pages to type any questions or comments that you have in the live chat on that lessons page, perhaps start a discussion with other students in which I will also respond. Obviously, if you're watching this elsewhere, such as on YouTube, then as always, you can type your questions into the comments and I'll be happy to get back to you with a response there as well. Okay, so let's start with the concept of a fuel in order to exemplify a very familiar type of exothermic reaction. So the first question that we need to answer is, what actually is a fuel to a chemist? Now, obviously, the concept of a fuel is something that's been familiar with us from the very earliest origins of human civilization. The idea that the invention of fire was one of the key discoveries that led to the setting up of human civilization is quite a ubiquitous idea. So what actually is a fuel then? Well, fuels are used in a number of contexts. Every day we use energy in our homes, in our schools, in our workplaces. This includes electrical energy, and much of that energy is produced by the combustion, the burning of fuels. So at home, we might burn fuels, such as in this photograph here, where we're burning wood in a wood fire. We burn these fuels to provide warmth and also sometimes to cook our foods. But in power stations, fossil fuels, for example, such as coal, oil, and natural gas, these are burned in order to produce heat energy, which can then be used to generate electrical energy. So we can define a fuel simply as a substance which burns in air to produce heat. Now, whether or not that fuel is going to be particularly useful for a particular application will depend upon how efficiently that fuel burns in air. Many substances will burn and can therefore, strictly speaking, be categorized as fuels, but not all substances will burn efficiently, and not all substances will produce a particularly good heat energy output. Some may produce harmful byproducts that we don't want in our homes, for example, and so some fuels are going to be more useful than others. So as I say, three of the most important fuels, and we will be encountering these again when we look at the next topic on organic chemistry. These are the so-called fossil fuels. So we have coal, we have oil, and we have natural gas or methane. So what do all these fuels have in common then? Well, all of these fuels typically contain the elements carbon and hydrogen. So compounds that are made up only of carbon and hydrogen are referred to as hydrocarbons. Again, we're going to be looking at those in the next topic when we encounter organic chemistry. But essentially, when these fuels burn in oxygen, they are undergoing an oxidation reaction involving the chemical bonding of those elements, carbon and hydrogen, with oxygen. So, as such, we're going to be producing the oxides of carbon and hydrogen, which are, of course, carbon dioxide and water. And in doing this, we release heat energy from that combustion reaction. And so, as heat energy is given out, this is referred to as an exothermic reaction. Exo from the word meaning outside or outwards, and thermic meaning to do with heat. So, we have for example, if we're burning methane, which is the main component of natural gas, methane has the chemical formula CH4. It is a hydrocarbon. So the chemical equation for the combustion, the complete combustion of methane in excess oxygen, is shown here. Now, strictly speaking, you shouldn't really put energy as part of a chemical equation. Energy is not a chemical substance, and so strictly speaking, you shouldn't include this. I include this here just to illustrate the fact that energy is there is a net energy output for this reaction. And so we have here a fuel, in this case a hydrocarbon fuel, methane. It's reacting with molecular atmospheric oxygen, and it's producing carbon dioxide gas, water gas, and an output, a net output of energy. So this is an example of combustion. Now, there is a similar reaction happening in the cells of all of your body cells. Now, it's similar in the sense that it is an oxidation reaction in which a compound is being oxidized to produce carbon dioxide, water, and a net energy output. And this is the sequence of reactions that we call aerobic respiration. Now, it's similar in the sense that it is an oxidation reaction. It is quite different in a number of other respects, as we'll see. So every day, the world requires energy equivalent to approximately 200 million barrels of oil. And so this gives you a sense of the scope of the petrochemical industry and the requirement for energy output. So this pie chart here shows the energy provided by a range of fuels and other energy sources, and this is going back to about 2000. The figures are somewhat similar today. They're slightly different now, but they're somewhat similar, and this gives you a sense that the majority of the world's energy needs are provided for by the combustion of various types of fossil fuels. So we have here oil, we have natural gas, and we have also coal. So we can see here that together these three fossil fuels are responsible for the majority of the energy that we actually consume, whether that's electrical energy or simply energy produced in the combustion engines of cars and other vehicles. So, for example, every year in the UK, we require energy equivalent to that provided by over 300 million tonnes of coal. Now, to this day, coal is still the predominant fossil fuel used in fossil fuel burning power stations in the UK. So I mentioned respiration. The foods that we eat typically contain large numbers of carbon and hydrogen atoms because biological macromolecules that we have in our foods, such as proteins, carbohydrates, and lipids, are organic molecules. They are biopolymers which are based around carbon chemistry, and so they do have a rather large quantity of carbon and hydrogen in them by mass. Now, in particular, the nutrients that we use typically for as a source of energy would be carbohydrates preferentially, and then lipids. So essentially, these are the so-called fuels for respiration. Now, I use the word fuel here advisedly. There isn't actually combustion happening inside your cells. It's a different kind of oxidation reaction. And so often you'll hear people throw around the term fuel in reference to food. And it's kind of it's an analogous concept, but it's not quite the same thing. And again, we defined fuels as a chemist as being substances that we burn or combust in oxygen to produce a useful heat energy output. But essentially it's an oxidation reaction where you have the food chemically combining with oxygen to produce carbon dioxide, water, and energy output, much of which is dissipated as heat. So when humans inhale air, air enters the lungs, and from the lungs, oxygen in the inhaled air will dissolve across the alveoli, across the capillaries of the lungs into the blood. The heart then pumps that oxygenated blood to the tissues where the oxygen diffuses out and into the body cells and is used for aerobic respiration. So in respiration, the actual so-called fuel is glucose, a type of monosaccharide or sugar. Now, the body can also metabolize fats and oils by converting them into sugars if necessary. So the actual overall chemical equation for respiration is this one here. We have glucose sugar combining with oxygen to form carbon dioxide, water, and a net energy output. Now, again, this is an oxidation reaction, but it is not combustion. This is actually a summary. This one reaction or this one equation actually summarizes a sequence of chemical reactions that happens inside cells, each of which is enzyme catalyzed. But at GCSE level, you don't need to know the specifics of the individual reactions involved, but you do need to know that this doesn't happen in one chemical step. This equation is a summary of a number of different chemical reactions that gets you from these reactants ultimately to these products. So how do we actually measure the energy content in food and in fuels? Well, for this we need a technique that we call calorimetry. But first we need to remind ourselves that the energy is measured in units called joules, which are the standard units, or if we're measuring in thousands of joules, we would give them as kilojoules. So dietary information about the energy content in food is typically found on food packaging and sometimes is given in non-standard units called calories or thousands of calories, in which case we use the term kilocalories. Now, 1 calorie is equal to 4.2 joules, so there's the equivalency. So in order to measure the amount of energy content of food, we use a device and a technique that we call calorimetry. So let's take a look at how we would use a calorimeter to do this. Now, a basic calorimeter, which perhaps you might have used yourself in either biology or chemistry lessons, may look a little bit like this. So this is a rather simple method for calculating the amount of chemical potential energy in a food or a fuel, and the way that we do this is we simply take the piece of food which we have measured the mass of and we burn it to release heat energy, and the flame from the food is used to heat a known volume of water from a known starting temperature, and as soon as all of the combustion is complete, we measure the final temperature, and then we can use an equation to work out how much heat energy was given to the water by the burning fuel. by the burning food rather. And then since we know the mass of the food, we can then calculate the number of joules of energy that were originally stored per gram of that food. So essentially, we are burning a small amount of food, and we're using the heat from that burning process to heat a known mass of water. So typically in the laboratory, pasta like this is a very good type of food to test because pasta is rich in carbohydrates and typically has a high energy content. So let's take a closer look at this apparatus here. So we have the boiling tube suspended above where the pasta is, and we're about to set light to the pasta. We position it underneath the boiling tube so that when it does start to burn, the flame will heat the bottom of the boiling tube. Now what we also have here is this loop of metal here, which we can grab onto at this end. This is a stirring rod. We can simply raise this up and down through the water to keep it stirring, to distribute the thermal energy evenly through that volume of water. We have a cotton wool plug here, and we also have a thermometer to monitor the rise in temperature which is achieved by the burning of the fuel. So typically we would use a known quantity of water. In this case we're using 20 centimeters cubed of water. Now remember that water has a density of 1 gram per cubic centimeter, and so if we know the volume of the water in centimeters cubed, it's numerically equal to its mass in grams. So we suspend the pasta by a drawing pin which is placed upon a lump of plasticine, and this allows the pasta to burn completely, the top and the bottom of it as well. So essentially we take 20 centimeters cubed or 20 grams of water, we place it into a boiling tube and we clamp this upright. We record the mass of the food being burned, and we take the initial temperature of the water and record that as well before we start to burn the food. Now, we then hold the pasta in a Bunsen flame until it burns, and then we support it beneath the boiling tube as shown here. Now, continuously while the pasta is burning, we gently stir the water by raising and lowering the stirrer, and then once the pasta is finished burning, we record the highest temperature reached by the water. So it may be that once the pasta stops burning, the temperature on the thermometer continues to rise somewhat. So it's important to record the highest temperature reached. So let's say we did this experiment. How would we actually calculate from these measurements the amount of energy that was stored in the pasta? Well, imagine that we used 0.2 grams of pasta and we again heated 20 centimeters cubed of water. And let's just say that the starting temperature was 20 degrees centigrade and the final temperature was 45 degrees centigrade. This would give us a temperature rise of 25 degrees centigrade. Now the equation that we're going to use is the equation that involves heating and cooling a substance when we know its specific heat capacity. Excuse me, I'm still recovering from a bit of a cold, sorry guys. So the equation is something that you will have come across probably in GCSE physics. The heat energy change involved when something is increasing or decreasing in temperature is equal to its mass multiplied by its specific heat capacity multiplied by the change in temperature that occurs. So this is essentially the same equation, but in this case we are measuring the mass in non-standard units of grams rather than kilograms. The specific heat capacity of water in joules per gram per degree centigrade is 4.2 joules of heat energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And so this is the equation that we're going to use. So we can calculate the energy that was absorbed by the water by taking the mass of the water, which is 20 grams. Again, 1 centimeter cubed of water will have a density of will have a mass of 1 gram because the density of water is 1 gram per cubic centimeter. So if we have 20 centimeters cubed of water, we have a mass of water of 20 grams. The temperature rise, we multiply that by is 25 degrees centigrade. We then multiply that by the specific heat capacity of water, which is 4.2 joules per gram per degree centigrade. And this gives us an energy change of 2,100 joules. So this tells us that 2.1 kilojoules of heat energy was absorbed by the water in order to cause that 25 degrees centigrade rise in temperature. Now we had 0.2 grams of pasta. So if we wanted to calculate how many kilojoules of energy there were per gram of pasta, we would divide this energy content by the number of grams of pasta that we had. So we would get this 2.1 from 0.2 grams of pasta gives us this value here. So we divide 2.1 kilojoules by 0.2 and we get 10.5 kilojoules per gram, which equates to 1050 kilojoules per 100 grams. Now I include this line here because typically the energy content of food is expressed per 100 grams of food. So now we also need to know some of the actual features of the experiment. So this is essentially demonstrating the procedure that we've already talked about. So we can see the temperature rise here. So you might want to consider at this point what would be the sources of error in this investigation. So let's take a look at those now. Now, in the example of the experimental setup that we've just seen, again, I stress that that's a very simplified example. Obviously, we have a source of error in that not all the heat energy given off by the burning of the pasta goes into the water itself. Obviously, some of it is going to be lost into the surroundings. And so heat is going to be used, heat is going to be lost around the edges of the test tube. It's going to be used also in warming up the glass of the test tube and also the other components of the calorimeter itself. There's also the fact that the pasta may not burn completely. You may not have complete combustion, you may have incomplete combustion, which means you haven't actually released all of the chemical potential energy in the fuel. You also have heat losses occurring from the water itself through the glass and the cotton wool plug into the surroundings. Now, these are the kinds of errors that you might expect from that rather simplified experimental setup, which is why in the food industry and also in the laboratory, when we're measuring the energy content by doing combustion, we use a much more precise, much more accurate measuring device called a bomb calorimeter. So the way that this works is that, again, it's the same principle, but in this case, rather than using atmospheric oxygen, we place a known dry mass of the food into an atmosphere of pure oxygen within the calorimeter. Now, the material is ignited using an electrical discharge, and the heat produced is passed almost entirely to the known mass of water, and the rise in temperature again is recorded. Now, the bomb calorimeter is much more accurate, partly because of these reasons and partly also because of the design of the device. So, here we can see the design of a bomb calorimeter. So once again, we have a stirrer. We have the lid of the calorimeter, which is insulated. We have a known measured volume of water. Now, inside this chamber, we have an inner chamber. This is actually where the combustion of the food substance takes place. The way that this works is that we have an electrical heating coil here, and we have, again, an insulated base, typically made of asbestos or some other insulating heat retardant material. We pump into this inner chamber pure oxygen gas. And the waste gas is exhausted through this copper pipe, which is coiled multiple times so that any heat from the exhaust gases is radiated and conducted into the surrounding water, and therefore also contributes to the measured rise in temperature of the water. Inside this little crucible is where we have the measured mass of the food sample, and the food sample is very carefully dried beforehand. So inside this chamber we have pure oxygen for complete combustion. And of course we have a thermometer with which to measure the rise in temperature of this known volume, this known mass of water. So this is the bomb calorimeter, and as you can see, it's a rather more sophisticated device which is designed to minimize those sources of error. So let's take a look at some results from using a bomb calorimeter here. So these are typical energy content values from 100 grams of various different kinds of food. So these show that the crisps released the largest amount of energy among these foods. So the reason for this is that the crisps contain typically a very high fat content, and fats do actually contain by mass a lot more chemical potential energy than typical carbohydrates. Now, the biological implications of this, obviously we will explore in more detail in the biology course, but for now we can say that this is part of the reason why eating too many fatty foods is bad for you. Not only can they lead to the clogging of the arteries, atherosclerosis, but the energy content is so high that ultimately your body cannot actually utilize all of that energy, and so it ends up storing it as subcutaneous fat, and this can lead to obesity. So we've looked at a number of different contexts here. We've looked at how we can measure the energy changes of reactions. So let's take a look at the different kinds of reaction categorized as to whether or not they give energy out into the surroundings or whether they take energy in from the surroundings. So if we wanted to study the energy change in an exothermic reaction, the reaction can be made to take place in an insulated container such as a bomb calorimeter, and the temperature can then be measured. So for example, if we're doing a neutralization reaction between an acid such as sulfuric acid and an alkali such as sodium hydroxide, we would expect an exothermic reaction. Typically, neutralization reactions are exothermic. This means that when we do the neutralization reaction, when we mix our alkali solution with our acid solution and the neutralization takes place, we would expect that reaction mixture, that solution, to increase in temperature. And so this can be demonstrated experimentally, and we can measure that rise in temperature. But what does this actually mean in terms of energy changes? Well, energy, remember, is conserved, which means that the total energy that you start with in any system, whether you're considering objects in motion, whether you're considering a chemical reaction or an electrical system, any system undergoing change will always have the same total energy to start with as it has to end up with. The only thing that changes is the way in which that energy is stored within the system or transferred within the system. So the way that we represent these changes is by means of energy level diagrams or reaction profiles. And so what we see here is a reaction profile for an exothermic reaction. A reaction is exothermic when it releases energy. Now what that means is that the reactants to begin with had more chemical potential energy stored in them than the products that you end up with, which means that if the energy level of the reactants is here, and the energy level of the products is here, the difference in energy doesn't just disappear. In going from the reactants to the products, we're going from higher energy to lower energy. And so we say that the enthalpy change, or the chemical potential energy change, delta H, is negative. We're going from a higher value to a lower value. So this is how we would illustrate a exothermic reaction. Now, as we'll see a bit later on, the reason for this is because the difference in the energy required to break all of the chemical bonds in the reactants versus the energy released when the new chemical bonds form to make the products causes a net output of energy. And so we can say that in exothermic reactions, there is a net release of energy into the surroundings, and in this case that means into the reaction mixture, causing the reaction mixture to increase in temperature. Ultimately, that heat energy is going to be radiated and conducted into the surroundings. So the reason for this is because the total energy stored in the chemical bonds in the products is less than the total energy stored in the chemical bonds of the reactants. Now let's take a closer look at that reaction profile. Now you might have noticed in the previous diagram, there's the energy level doesn't go straight from the reactants to the products. It increases slightly first and then goes downwards. Now the reason for this is that there needs to be a small amount of energy put into the reaction or put into the reactants to start the reaction off. This is called the activation energy, and this is the energy required to start breaking the bonds in the reactants so that those atoms can then reorganize to form the products. And so the reaction profile for an exothermic reaction looks like this. The reactants start off at a higher energy than the products. Some energy is put into the reaction. This causes the chemical bonds between the atoms in the reactant molecules to break. Then, once those atoms have broken their chemical bonds with each other, they can start to form new chemical bonds to form the products. And that process is an exothermic process. Energy is always released when chemical bonds are made because atoms are achieving stability by forming those chemical bonds. Again, if you want more details on that, I would suggest going back to the topic on chemical bonding when we talked about atomic not atomic, ionic and covalent bonding in the second topic of this course. Remember that atoms form chemical bonds with each other in order to achieve stability. Unstable atoms with incomplete outer shells are at a higher level of potential energy than atoms which have completed their outer shells by forming chemical bonds with each other. So bond making is an exothermic process. It releases heat energy to the surroundings. To break chemical bonds, you have to put energy in. It's an endothermic process because you're taking more stable atoms bonded together and splitting them apart and putting them into an unstable condition. So in an exothermic reaction, the net chemical potential energy change that we call delta H, which stands for change in enthalpy. Enthalpy, which the symbol is H in chemistry. Enthalpy is another way of saying chemical potential energy stored in a system of in a chemical system. So in exothermic reactions, the net energy change, the net enthalpy change is from higher to lower, and this is negative. So we can see here the relationships between the amount of energy needed to break the existing bonds and the amount of energy released when the new bonds are made. The difference between these two is the overall enthalpy change for the reaction. Now, since in this case we're going from higher to lower, this change is defined as being negative. So in an exothermic reaction, the products are at a lower chemical potential energy than the reactants. The difference in height on this diagram between the reactants and products represents, in this case, the energy given out in going from these higher potential energy reactants to these lower chemical potential energy products. So let's take a look at an example of exothermic reactions. So let's take a look at what happens when we burn carbon in excess oxygen to produce carbon dioxide. Well, the reactants in this case are carbon and oxygen. The product in this case is carbon dioxide. So when we take 1 mole of carbon, which has a mass of 12 grams, and we burn it in excess oxygen, the net enthalpy change is that 394 kilojoules of heat is given out by that reaction. So here we can see the overall enthalpy change for this reaction is given a negative value because relative to the reactants, the products are at a lower potential energy level than the reactants. So in a later lesson of this topic, we're going to be looking at the role of catalysts in speeding up chemical reactions, and as we'll see, catalysts do so by changing the reaction profile, by changing the amount of activation energy required and making it lower. So when a catalyst is added to an exothermic reaction, it lowers the activation energy required for that reaction. Now again, we're going to be looking at catalysts in a lot more detail in a later lesson, but for now let's take a look at what happens to that last reaction that we saw when we add a catalyst. Now without a catalyst, we can see here that the amount of activation energy required to get the reaction to start to go is much higher without a catalyst than it is with a catalyst. And this means less energy is required to start the reaction by breaking the chemical bonds in the reactants when you have a catalyst present than when you have no catalyst present. Now, what about endothermic reactions then? Well, we can measure the enthalpy change or the energy change in an endothermic reaction in the same way. We can monitor the temperature change of the reaction mixture as that reaction happens. So, for example, if we dissolve ammonium hydroxide in water, we find that the temperature of that solution that's created actually decreases. And this indicates an endothermic reaction has taken place. So let's take a look at how we would represent one of these endothermic reactions using a reaction profile diagram. This is how we would do it. So in an endothermic reaction, energy is taken in. There is a net input of energy in going from the reactants to the products, because in this case, the chemical potential energy in the products is higher than the chemical potential energy in the reactants. So the net change in going from the reactants to products is positive. We're going from a lower value to a higher value of enthalpy. Now, as we can see here, again, the reaction doesn't go straight from this level of energy to this level of energy. There is an amount of energy that needs to be put in, and again, this is called the activation energy. Now, overall, in an endothermic reaction, as I've said before in the previous slide, delta H, the enthalpy change, is positive. However, in this case, the activation energy required takes us all the way from our reactants to this point here, when all of the bonds in the reactants have broken and new bonds start to be made. So, in this case, this value here with this blue arrow, this change here, is the activation energy. The energy needed to break the bonds in the reactants takes us to this level of energy. At this point, the atoms that we've separated from each other start to form new bonds to form the products. And so the energy change in forming the new bonds to form the products is from this level to this level here. So this is the energy change, which again is exothermic. Remember, bond making is exothermic because you're going from less stable unbonded atoms to more stable bonded atoms. So this would be the enthalpy diagram for an endothermic reaction. In an endothermic reaction, the products are at a higher potential energy level than the reactants. And again, on the diagram, the difference along the vertical axis between where the reactants are and where the products are is the overall change for the reaction. So we're going up in this direction with the activation energy being provided, and then we're going back in this direction when new energy is being released when the new bonds are being made. And so the difference between this increase and this decrease is the overall enthalpy change for the reaction. And so in this case, it's positive because we've gone from a lower level in the reactants to a higher level in the products. So let's take a look at an example of an endothermic reaction. So here we can see the reactant ammonia. And what happens when we break down ammonia back into its elements, nitrogen and hydrogen? Well, when 1 mole of ammonia decomposes to give nitrogen and hydrogen, 93 kilojoules of heat is required to be put into that process in order to get to the products. So here we can see that the enthalpy change for the reaction is positive. We had to put in net 93 kilojoules to decompose 1 mole of ammonia to its elements, nitrogen and hydrogen. So what role do catalysts play in endothermic reactions? Well, once again, catalysts will decrease the activation energy required to get an endothermic reaction to go. And the way that we can represent this is by means of this energy level diagram here. So we can see here that without a catalyst, the activation energy barrier is much higher. With a catalyst present, the activation energy barrier is much lower. And so, with a catalyst present, less energy has to be put in order to get the bonds in the reactants to break apart before the products can start to be formed. And this overall increases the rate of reaction. Now you'll notice in both exothermic and endothermic reactions, whether you have a catalyst or not, the overall enthalpy change for the reaction delta H is not affected. What is affected is the amount of energy required to initiate the reaction, the activation energy. In both cases, in endothermic and exothermic reactions, you require less energy you require less activation energy to start the reaction if you have a catalyst present. So how do we explain all of this? Well, again, it goes back to this idea that chemical bonds have a bond energy associated with them. Now, this value is pretty much the same no matter what compound the bond occurs in. Known bond energies can be used to calculate the overall energy change for a reaction. Now remember, when a chemical reaction occurs, the first thing that needs to happen is that the chemical bonds between the atoms in the reactants have to be broken. This has to happen because new chemical bonds have to be made between those atoms in order to form the products. So, Essentially, the overall energy change for the reaction depends upon the difference between the amount of energy you have to put in to break the bonds in the reactants and the amount of energy you get out of the chemical reaction when the new bonds are made. Bond breaking is an endothermic process because energy is used to pull apart those reactant molecules and split apart those atoms to break the chemical bonds between them. So this is an endothermic process. Now, when you form new bonds between unbonded atoms typically have incomplete outer shells of electrons, and so they are unstable. Now, going back to what I've mentioned to you guys multiple times, whenever you hear the word stability or instability mentioned in pretty much any scientific context, typically unstable or instability is associated with a system in a high state of potential energy. Stability is when that system has achieved a relatively lower level of potential energy. And so, if you're going from unstable, unbonded atoms to stable or more stable bonded atoms, the process is going from a system containing a high amount of stored energy to a low amount of stored energy. And that essentially means that energy must be given out. So bond forming, bond making, going from the unbonded atoms to the products is exothermic. Energy is given out when we make more stable product molecules from the unbonded atoms that we got to by breaking the atoms apart in our reactants. And so bond forming is exothermic. Now, what this means is the bond breaking, being endothermic, will have an overall positive value in terms of the energy required. It's positive because energy needs to be put into the system to break those bonds. Conversely, bond forming, the amount of energy given off by the reaction when the bonds are formed to make the products, this will have a negative value in kilojoules per mole because, again, the system is giving off energy into its surroundings. So let's take a look at some examples of how we would calculate the overall energy change or enthalpy change for a reaction from bond energy values. So let's say we're taking a look at the formation of hydrogen chloride, HCl, from its elements, hydrogen and chlorine. So the reaction, the balanced simple equation for this reaction is shown here. We have hydrogen gas and chlorine gas combining to form hydrogen chloride gas. So we have the bonds between the hydrogen atoms in the molecules of hydrogen gas, and we have the bonds between the chlorine atoms in the molecules of chlorine gas. Now you'll notice that in the reactants we have no bonds between hydrogen and chlorine atoms. Conversely, in the product we have only chemical bonds between hydrogen and chlorine. We have no chlorine to chlorine bonds, we have no hydrogen to hydrogen bonds. So to get from here to here, we have to break the hydrogen to hydrogen bonds and the chlorine to chlorine bonds, and we need to make new hydrogen to chlorine bonds. So the breaking of these bonds requires energy, it's an endothermic process, and the formation of these new hydrogen to chlorine chemical bonds will be an exothermic process, it will give out energy. Now the bond enthalpy values are known values that you can look up in reference text, you can look them up online, these are standard values. So the way that we would do this is we first need to identify which bonds are being broken in our reactants and which new bonds are being made in our product, and also how many moles of each are being formed and broken. So in the previous reaction, we looked at hydrogen to hydrogen bonds. Hydrogen to hydrogen bonds have a bond energy value in kilojoules per mole of 436. Now what this means is to break 1 mole of hydrogen to hydrogen chemical bonds, you require 436 kilojoules of energy to be put in to break those bonds. The chlorine to chlorine bond enthalpy is 242 kilojoules per mole, and the hydrogen to chlorine bond enthalpy, the bonds that we're forming to make our product, has a bond energy of 431 kilojoules per mole. Now, since we're forming these bonds, in the particular reaction that we're looking at, this will have a negative value. So let's take a look at the calculation. So in terms of the bonds that we're breaking, again, looking back at the chemical equation, we have 1 mole of hydrogen molecules, each of which contains 1 mole of hydrogen to hydrogen bonds. So we require 436 kilojoules to break that 1 mole of bonds. We also have 1 mole of Cl2 molecules, which again contains 1 mole of chlorine to chlorine bonds. And so to break those bonds, we need 242 kilojoules. So the total amount of energy that we need to put in to break all of the existing bonds in the reactants is going to be this value plus this value, which gives us 678 kilojoules. Now, in contrast, on the right-hand side of that balance symbol equation, we had 2 moles of hydrogen chloride molecules. This means that we need to form 2 moles of H to Cl bonds. So we're going to release 2 times this value of energy in kilojoules in forming those bonds. So delta H, whenever you're calculating the overall enthalpy change from bond energy values, you need to remember that delta H is always the energy needed to break the bonds minus the energy released when the new bonds form. Now, this means that our delta H value for this reaction is going to be 678 minus 862. This gives us an overall enthalpy change for the reaction of minus 184 kilojoules. So this value tells us that it's an exothermic reaction because the value is negative. This tells us that the products are at a lower potential energy than the reactants, and therefore this quantity of energy, the difference in the potential energy of the products compared to the reactants, is going to be given off to the surroundings, and this will manifest itself as a rise in temperature of the reaction mixture. Let's take a look at another example here. So consider the reaction between methane and oxygen, the burning of methane in excess oxygen to produce carbon dioxide and water. Again, the equation for this reaction we've seen before is this. 1 mole of methane gas will react with 2 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles of water. So how would we calculate the energy for this reaction? Well, first we need the bond enthalpies, which means we first need to identify which chemical bonds are actually present in our reactants and our products. So methane is CH4. This means in 1 mole of methane, we're going to have 4 moles of carbon to hydrogen bonds. So we need the value for carbon to hydrogen bonds. The bond enthalpy for carbon to hydrogen bonds is 413 kilojoules per mole. Now, oxygen molecules are diatomic molecules which contain an oxygen to oxygen double bond. If you want to know why that's the case, I'd suggest going back to the first topic where we looked at the positions of the group 6 elements in the periodic table, and also the second topic on structure and bonding where we looked at covalent simple molecules such as oxygen and the idea of double covalent bonds. So oxygen, O2, is 2 oxygen atoms double bonded. Now the oxygen to oxygen double bond has a bond enthalpy of 498 kilojoules per mole. Carbon dioxide, again, the structure of this is a carbon double bonded to 1 oxygen and then double bonded to another oxygen. And so we need the bond enthalpy for the carbon to oxygen double bond, which is this, 803 kilojoules per mole. Water contains 1 oxygen atom covalently bonded by a single bond to 1 hydrogen and also by another single bond to another hydrogen. So we need the bond enthalpy value for oxygen to hydrogen single bonds, and that is 464 kilojoules per mole. So now that we've identified which bonds are present in our reactants and products, and we have the bond enthalpy values, we can apply the same logic as we saw in the previous example to solve this problem. So let's take a look at which bonds are being broken. Well, 1 methane molecule contains 4 carbon to hydrogen single bonds, so we need to put in 4 times 413 kilojoules to break those bonds. This gives us a total input value of 1,652 kilojoules to break all of the bonds in our methane molecules. We have 2 moles of oxygen molecules in the balance symbol equation in the reactant, so we need to break 2 moles of oxygen to oxygen double bonds. This gives us a total input value of 996 kilojoules. So to break all of the bonds in our reactants, we need a total of 2,648 kilojoules of energy. So now let's take a look at what happens when we form the bonds in our products. So again, we have 1 mole of carbon dioxide molecules, but each mole of carbon dioxide molecules contains 2 moles of carbon to oxygen double bonds. Remember, each molecule of carbon dioxide contains 1 carbon double bonded to 2 oxygens, so that there are 2 carbon to oxygen double bonds in each molecule of carbon dioxide. So the total energy required to break those 2 moles of carbon to oxygen double bonds is going to be 2 times 803, which gives us or rather the energy released when we form those 2 moles of carbon to oxygen double bonds will be 1,606 kilojoules. We're also forming 2 moles of water molecules. Now, each mole of water molecules contains 2 moles of oxygen to hydrogen single bonds, and therefore the total energy released when we form all of those bonds is going to be 4 times the value for oxygen to hydrogen bonds. This gives us a total energy release for that of 1,856, which means the total amount of energy released when we form the new chemical bonds to make our products will be 3,462 kilojoules. So the overall enthalpy change for the reaction, again, is going to be the energy needed to break the bonds minus the energy released when we make the new chemical bonds to form our products. So we substitute those values in, and we find the overall enthalpy change for the reaction is minus 814 kilojoules. So we can see here from the negative value, again, that this is an exothermic reaction. Let's take a look at one more example here. So let's take a look at the dissociation reaction of ammonia to form nitrogen and hydrogen. So again, this time we have ammonia dissociating to form hydrogen and nitrogen here. So how would we calculate the energy change for this reaction given the bond enthalpies? So here we have the bond enthalpies for the hydrogen to hydrogen bond. We have the bond enthalpy for the nitrogen to nitrogen triple bond. Again, nitrogen is a diatomic molecule which contains 2 atoms of nitrogen triple covalently bonded together. So there's a triple covalent bond between these 2 atoms. The bond enthalpy for this is 942 kilojoules per mole of bonds. And finally, we have the nitrogen to hydrogen single covalent bond, which has a bond enthalpy of 388 kilojoules per mole. So let's take a look at how we do this. So again, we need to consider how many moles of bonds are we breaking and how many moles of bonds are we forming. So in terms of the reactants, there's only one reactant, it's ammonia. Ammonia has the formula NH3, which means that in every mole of ammonia molecules, there are 3 moles of nitrogen to hydrogen single bonds. So if we have 2 moles of ammonia molecules, as we saw on the left-hand side of the balance symbol equation, we will have a total of 6 moles of nitrogen to hydrogen bonds that we need to break. So in order to do that, we need 6 times the bond enthalpy for the nitrogen to hydrogen single bond. This gives us a total input of energy that required of 2,328 kilojoules. Now, in terms of the products, in order to form the products, we need to form hydrogen to hydrogen bonds, and we also need to form nitrogen to nitrogen triple bonds. Well, we're forming 3 moles of hydrogen gas, which means we need 3 times the hydrogen to hydrogen single covalent bond enthalpy. So the value that we need, that we're going to be releasing in the formation of our 3 moles of hydrogen gas is going to be 1,293 kilojoules. We're also forming 1 mole of nitrogen gas, which will contain 1 mole of nitrogen to nitrogen triple bonds. So in doing that, we're going to release 942 kilojoules. So the total amount of energy released when we form the new bonds to make our products is going to be this value plus this value, which gives us 2,235 kilojoules. So to calculate the overall enthalpy change for the reaction, we subtract the energy released when new bonds form from the energy needed to break the bonds in the first place in the reactants. So we substitute our values into this expression, and we have a overall enthalpy change of 93 kilojoules. Now this means, because it's positive, that energy needs to be put in to this reaction to thermally decompose ammonia into its elements, nitrogen and hydrogen. And so we would describe this as an endothermic reaction. Okay everyone, that's going to do it for the recorded segment of this lesson. I hope that was useful to you. I'm going to get into the Q&A discussion that I have with the students that I have in attendance with me now. Once again, thanks for watching, and I'll see you in the next one. Take care.